Hello everyone. I hope everyone is enjoying ICFP. And to those of you who are attending ICFP in person, I hope you are also enjoying Ljubljana. Unfortunately, I cannot attend this year's ICFP in person, but I'm nonetheless happy to be here virtually and present our paper Program Adverbs and Tlon Embeddings. My name is Yao Li. I'm assistant professor at Portland State University. This is work that was done when I was a PhD student at the University of Pennsylvania, in collaboration with my advisor Stephanie, who is attending ICFP in person. So let us start the talk. Suppose you want to verify an existing program. The original program might be written in C, Haskell, Verilog, or Makefile, etc., which are all mainstream languages that do not support mechanized reasoning. The first step you need to do is embedding such a program in a language that is amenable to mechanized reasoning, such as Isabelle, HOL in F star, or Calc. The step is known as semantic embedding, or simply embedding. It turns out embedding is with many challenges. First, we would like our embedding to be simple. So both developing the embedding procedures and working with the embedding might be easier. For example, let's consider the following arithmetic expression, 1 plus 2 plus 3 in Haskell, and let's embed the expression in Calc. We can either do a shallow embedding, which would look like the same expression, or a deep embedding, which would be an abstract syntax tree of the expression. The shallow embedding is simpler, and it makes reasoning about certain properties simpler as well. For example, we can easily show that 1 plus 2 plus 3 equals to 2 plus 3 plus 1, and also equals to 6. This is because these expressions are direct computable arithmetic expressions in Calc as well. So we get these theories of numbers, etc. built in Calc for free. On the other hand, we need either some extra theory for the EST or an interpretation from the EST to a shallow embedding to show the same thing for deep embedding. However, what is convenient in one situation can become inconvenient in another. Suppose we want to reason about properties related to the syntactic structures of the original program instead, such as how many plus operations does an expression contain. We would not be able to do so with a shallow embedding. We cannot tell the difference between 1 plus 2 plus 3 and 6 in our shallow embedding. Instead, we need deep embeddings. This is the second challenge of embeddings. We want our embeddings to be simple, but also be suitable for the properties we want to reason about. Finally, we want our embedding to be modular. This is because many programming languages contain similar language constructs, features, or computation patterns. Let's consider Makefile and FPGA. They are very different languages, but they share some common characteristics. First, they both enforce a static control flow. In a Makefile, file dependencies are statically fixed, and an FPGA is hardwired. Furthermore, due to the nature of their static control flow, we can parallelize certain computation in them, as seen in Make-J and in an FPGA. Furthermore, Haskell is a library that automatically runs certain operations in parallel. It is written in Haskell, a language more expressive than Makefile and FPGA, as it allows dynamic control flows. But a particular piece of code in Haskell may only contain static control flow, and Haskell makes use of exactly that part to run parallel computation. In other words, Haskell also has a subset that shares these characteristics. We would like to model these shared characteristics in a modular way, so we don't need to repeat ourselves. This paper tries to address exactly these challenges, but in the context of reasoning about effectful languages. In other words, we aim to find a way that allows us to reason about as many properties of an effectful program as possible in a modular and simple way. Let's start with an example. Consider a circuit that can read from some external devices. In this circuit we show on the screen, we read from two external devices, X and Y, or just one device if they point to the same device. And join the value read from them with an AND gate. This circuit has a sturdy control flow and it runs in parallel. In addition, we might want to model the reading effects from external devices abstractly, either because we want to make the embedding modular, so it works with multiple different types of external devices, or simply because we do not know anything about these external devices. Note that reading effect on these external devices might do anything depending on the device. For example, each reading from us might change the values on the device, or the value changed by themselves every second, or the value returned are purely random. How do we model such a computation pattern? Our inspiration comes from many previous works on free or freer monads and their variants, such as interaction trees, which allows us to embed effects using an uninterpreted data type. We have discussed earlier shallow embeddings and deep embeddings and their trade-offs in terms of properties. These two styles of embedding are common choices when we embed a program, but they are not the only two. In fact, as many recent research work show, the style of embedding should be viewed as a spectrum rather than a binary choice. Free monads and their variants offer a pretty good mixture for embedding effectful program in this spectrum. The mixture is embedding effects deeply as an uninterpreted algebraic data type, and embedding pure computation shallowly. In this paper, we generalize this key idea of free monads and propose a class of mixed embedding that capture general properties of computation patterns. We call this class of mixed embeddings Tlon embeddings. More specifically, two circuits. Free monads are too expressive to properly represent them. For example, monads would allow dynamic control flows, so using them would allow us to write exotic terms that cannot be expressed in the original language, and would get in our way if we would like to reason about properties related to this static nature. Now, before we move on, some of you might be wondering how to pronounce the word Tlon. And the rest of you might be wondering what Tlon even means. You can pronounce Tlon however you want, as it's a fictional word from a short story of Borges. If you want to learn why we use this word to describe this class of embedding, I promise you that there is an answer in our paper. Now, instead of using free monads in the circuits, we derive a structure from a different class of functors, namely applicative functors, as shown here. We derive the new structure by redefining applicative functors. First, we declare a data type parameterized by an effect data type called E and a return type called R. Then, we take every method from the class and make it a constructor and change the types accordingly. In the end, we add an embed constructor for embedding effects in it. The part that demands special attention here is the lift-A2 constructor, which contains two computations that do not rely on each other. There is no way to run a different computation or invoke different effects depending on the result of another computation effect. This structure is called a program adverb. With this program adverb, we can represent circuits shown earlier as follows. First, we use the lift-A2 constructor to represent the drawing of two reads. We use the Boolean AND function in calc to represent the AND gate. Then we use embed to embed the read effects, which is merely represented by uninterpreted constructors. This gives us an embedding of the circuit, which represents the pure computation shallowly, and deep embeddings and the effects deeply. Program adverbs are not just the data types. They also contain some general theories that can be used for reasoning about semantic properties, such as some parallel properties about the circuits. For the sake of time, We do not show adverb theories here, but you can find them in our paper. I found it useful to understand program adverbs in comparison with effects. By effects, I mean new operations that provide our program interaction with external environment. Like reading from external devices in a circuit, I/O, exception, mutable states, mutually exclusive locks, etc. If we make an analogy between program languages and natural languages, effects are like verbs in a natural language. However, verbs themselves do not decide how an action is done, as they can also be modified by adverbs. It is the same in programming languages. We have some computation patterns or general mechanisms that work on the control flow or data flow that would modify how an effect is invoked in a general way. These computation patterns include static or dynamic control flows, parallel execution and non-determinism, etc. Program adverbs are structures that capture exactly this type of computation patterns. So how do we find other program adverbs? It turns out we can derive many program adverbs by reifying the many classes of functors that are commonly used in Haskell, such as functors, applicative functor, which we have shown earlier, selective applicative functors, and monads. We give name in adverbial form for each of them, as shown on the screen. Okay, so far we've been talking about standalone adverbs. But what about the modularity concern we were talking about earlier? In particular, in a Haskell program, there is a subset that has static control flows and parallelization, and another subset that has dynamic control flows. To model programs like Haskell, we also need a way to compose different program adverbs. This pursuit, however, would lead us to the expression problem. In our paper, we overcome this problem by making use of the techniques presented by Delaware et al. In their semantic theory on a Carte paper, which builds on church encodings. By making program adverbs composable, we can actually achieve a computation pattern on a Carte approach that allow us to add existing program adverbs as needed. Furthermore, since program adverbs do not need to be standalone, we define a few more program adverbs that represent repeated computation and non-determinism that are mostly useful when combining with other computation patterns. We discuss these composable program adverbs in more detail in our paper, along with 2 case studies using composable program adverbs. One case study is based on the key ideas of Haskell, and the other one is about a networked server. You can also find our Coq source code in the artifact of our paper. In conclusion, in our paper, we present a class of mixed embeddings called Tlon Embeddings that allow us to embed programs using program adverbs. Program adverbs are structures that are parameterized by effects and can be interpreted into shallow embeddings. They model some common computation patterns, and they are composable, enabling composing computation patterns as needed according to the original language. Program adverbs can be used to reason about syntactic properties, as well as semantic properties about general computation patterns. And they can also be used to reason about semantic properties via an interpretation to shallow embeddings. You can find more detail about this in our paper. That is all for my talk today. Thanks for listening, and I'm happy to take questions.